All right, guys, Mr. Antonucci here, and in this video, we're going to talk about limits at infinity as well as horizontal asymptotes. So we're going to start off with limits at infinity, and this is a situation in which x itself becomes unbounded in the positive or negative direction. So if the function approaches a single finite value L, then that value of L is called the limit of f at infinity. We'll look at the limits at infinity for f of x equals 1 over x. What we'll do is we'll investigate what the graph looks like to get an idea of what the limit at infinity would be. Here's the graph, and if we look at x approaching positive infinity, that means the x value increases without bound. And if I look, the y values look like they start to level off at 0, which kind of makes sense if you think about what's going to happen numerically. If I let x approach infinity, and we can see that quickly the graph gets closer and closer to 0 as x approaches positive infinity. Similarly, if you go to negative infinity, you can see that the graph is going to approach 0 there as well. So this suggests that the limit at negative infinity of f is 0. So we would write the limit as x approaches infinity of f of x equals 0, and the limit as x approaches negative infinity of f of x equals 0. So here's a bunch of properties of limits for infinite limits, and these are pretty much the same properties that we looked at for regular limits. So limit of a constant, constant times a function, sum and difference, product, quotient, power, root, all of those. You don't need to memorize them, but it is good to know them. Also, you never want to substitute infinity into an expression for x. Infinity is a symbol that represents unboundedness, not a finite value, so you can't substitute infinity in for x. Two more helpful infinite limits are the limits for k over x to the p, where x approaches infinity, or negative infinity. Those are both 0. So based on these properties, we can find some limits here. As x approaches infinity, 5 over x cubed, the limit is 0 there. Think about positive 5, and the denominator is a number cubed, and that number is getting larger and larger. So 5 divided by a larger and larger and larger number is going to approach 0. Same thing with this one. You would have 0 here, and this follows from the limit properties, but also you can think about if you take the square root of a number that's getting larger and larger and larger, the answer's going to keep getting larger, and 1 divided by a larger and larger number is 0. Same thing's going to happen with these two down here. As x approaches negative infinity, x to the 1/3 approaches a larger and larger and larger negative number, and negative 6 divided by that is also going to be 0. And same thing's going to happen with this one. So this is just to illustrate those properties that we were looking at. A couple more examples here. These are a little bit more complicated, but in the situation with this first one, you can think of it as a limit as x approaches infinity of 2 plus the limit as x approaches infinity of 3 over x. Now, as x approaches infinity, the limit of a constant is that constant, plus 3 over x is going to go to 0. So you would have just plain old 2 here. And so you can kind of think through some of these. Here we have a product, and each product, one is a sum, one is a difference. So this first one, you have 2, which is a constant, so that's limit's going to be 2, plus 1 over x is the rational with the denominator being the variable, so that limit's going to be 0. And then in the second factor, we have 1/3, so the limit as x approaches infinity of the constant is the constant, minus, and then you have 2 over x cubed, which that limit's going to be 0 as well. So if you multiply that out, you would just end up with 2/3. One of the things that we can try to do is take the limit as x approaches infinity of the numerator and denominator. First thing we can do is factor out that 1/4. But if you take the limit of the numerator and the limit of the denominator, both of those are going to be infinite. And then you have infinity over infinity, which is another indeterminate form that's not just going to divide out to be 1. What you can do, however, is you have that 1/4, you can break apart the fraction into 3x squared over x squared plus 5x over x squared minus 1 over x squared. And then if you simplify that a little bit, you'd have 1/4 times the limit as x approaches infinity of 3 plus 5 over x minus 1 over x squared. And this one's going to go to 0, this one's going to go to 0, and this one is a constant, so it's just going to be 3. You multiply those out, you get 3/4. When you have an algebraic function that involves a quotient, one way to tackle this is to divide the numerator and denominator by the highest power of x in the denominator. So in this case, we're going to take the limit as x approaches infinity of x cubed over x cubed minus x to the 2/3 over x cubed. See how I'm dividing each term by x cubed. And the reason this is okay is because you're essentially multiplying by 1 over x cubed over 1 over x cubed and then distributing it to the numerator and denominator terms. And this is a fraction that is equivalent to 1. So this simplifies to, now if we take the limit as x approaches infinity, the numerator, both of these terms are going to approach 0. And in the denominator, you would have 1 minus 0. So that approaches 0. Now for this case, we want to divide the numerator and denominator by the highest power of x that appears in the denominator. The square root of x squared equals absolute value of x, which in this case is x because we're dealing with positive values. The divisor in the square root is going to be x squared. In other words, we'll take the limit as x approaches infinity of x over x minus 5 over x. And this entire quantity in the numerator is 4x squared plus 10 over x. And to get that inside of the square root, we would write that as square root x squared. And then we can combine those in the numerator and get square root of 4 plus 10 over x squared over 1 minus 5 over x. And now we'll take the limit as x approaches infinity here. The limit of a constant is just the constant 4. The 10 over x goes to 0, so you'd have square root of 4. In the denominator, 1 is the limit of a constant, which is 1. The 5 over x goes to 0, so you just have 1. Square root of 4 is 2. 2 over 1 is just 2. For polynomial and rational functions, it's even easier to find limits at infinity. For polynomials, you have to look at the term with the highest degree and its coefficient. For rational functions, you look at the ratio of those terms from the numerator and denominator. So here's some examples. If I take the limit as x approaches infinity of this polynomial here, you have a 3x cubed. So at infinity, these other terms are not going to really impact what happens as x approaches infinity. The x cubed is. And since x cubed is going to go off to infinity as x approaches infinity, and 3 will multiply that by 3, you're still going to have infinity. However, if the x had approached negative infinity, in this case, because when you cube a negative, you get a negative, the limit would be negative infinity. If the first term was negative 3x cubed and you took the limit as x approaches infinity, this would be negative infinity. A positive number cubed is positive, but you're multiplying it by negative 3, which is going to flip the sign to negative infinity. In this situation here, we have x approaching negative infinity. The highest degree term is 2x to the 4th. X to the 4th has an even exponent, so when you raise a negative number to an even power, the answer is positive. The leading coefficient is 2, which is also positive, so that limit is going to be infinity. Had the 2 been negative, the limit would be negative infinity. For this one over here, as x approaches infinity, the limit is infinity. The leading coefficient is understood to be 1. The power is 5, which is odd. A positive number raised to the 5th power is positive, and so we have a limit at infinity. In this case, we have x cubed as the term with the highest degree. If you cube a negative, you get a negative, so the limit is going to be negative infinity. For this one, as x approaches infinity, we look at the ratio of the leading terms for each one. So this is going to essentially be the limit as x approaches infinity of 3x squared over x squared. At infinity, these other terms aren't really going to make much of a difference at all. And so essentially the x squareds are going to have the most determining factors here. And since they're both x squareds, they're going to essentially even one another out, multiply by 3, and you would have 3. In this case here, the leading terms are 4x squared and x cubed. Since x cubed is growing faster than x squared, it's going to overpower it and force the problem to become smaller and smaller and smaller as x approaches infinity, so the limit in this case would be 0. And this last situation here, notice the leading terms are 5x to the 4th and 2x squared, and we're taking the limit as x approaches infinity here. And this one is going to be infinity. The numerator's degree is higher, so it grows faster. So it goes off to positive infinity. So in this case, the degree of the numerator and denominator were the same. So you have the ratio of the leading coefficients. In this example, the degree of the denominator was larger, so the limit ends up being 0. And in this last case, the degree of the numerator is larger, so you have infinite limit. Here's a couple other limits at infinity that are good to be familiar with. As x approaches negative infinity, e to the x goes to 0, and as x approaches infinity, e to the x approaches infinity. Also, as x approaches infinity, natural log of x approaches infinity. And you can't approach negative infinity, but another limit that may be helpful that we looked at earlier is x approaches 0 from the right of natural log x. That's going to be negative infinity. Now I want to talk about horizontal asymptotes and rational functions. So limits at infinity have an important geometric interpretation. The line y equals L is a horizontal asymptote of the graph of a function f if, as x approaches negative infinity, the limit is L. The line y equals m is a horizontal asymptote, and in this case, you're just approaching positive infinity. In other words, if you approach positive or negative infinity and the limit ends up being a finite number, then that line y equals whatever that number is a horizontal asymptote. A couple mistakes students are prone to make is make sure you check x approaching positive or negative infinity for horizontal asymptotes. Often students only check the positive one. The second thing is a function can have at most 2 horizontal asymptotes, but it can also have 1 or none. A function can have infinitely many vertical asymptotes. So that sometimes trips students up. So in the first case, we're going to take the limit as x approaches infinity, and that's going to be equal to 3/4. Because this is a rational function, the numerator and denominator have the highest degree being the same, so it's the leading coefficient. So the line y equals 3/4 is a horizontal asymptote. But you also want to check the limit as x approaches negative infinity. And in this case, you also get 3/4. So there's just one horizontal asymptote. Just wanted to show you what happens here if we put the line y equals 3/4 and we have the horizontal asymptote at y equals 3/4. And you can see it in the positive and the negative direction there. For this second one, we'll take the limit as x approaches positive infinity. Since the denominator has a degree that's higher than the numerator, this limit is automatically going to be 0. And same thing would happen for the limit as x approaches negative infinity. Y equals 0 is a horizontal asymptote. So here's the graph of the function, and you can see the horizontal asymptote at y equals 0. As x approaches positive infinity, we can see that it definitely levels off there. And at negative infinity, same thing. What trips students up is right here where this graph crosses its own horizontal asymptote. That is okay. A graph can cross its own horizontal asymptote. In fact, here's a situation, sine x over x, where as x approaches positive infinity or negative infinity, the horizontal asymptote is y equals 0. And this function actually crosses its own horizontal asymptote an infinite number of times. And then this last case, we have to be careful because the domain of this function is x greater than or equal to 2. If you go less than 2, this radical would end up having a negative number underneath the radical. So we can only look at the limit as x approaches infinity. Now the square root of x cubed is really the 3/2 degree. So that actually has the highest degree in it, which is 3/2. The denominator's degree is less than that. So the numerator has a higher degree, so the limit at infinity is going to be positive infinity. So just in summary here, in the second example, the graph crossed its own horizontal asymptote, and that's okay. However, a function's never going to cross its own vertical asymptote. In the third example, it's important to understand that x only approaches positive infinity because of the domain of that function. Another task you may have is to find any asymptotes of a rational function. So it's important to know how to show the work for this. So the first thing you want to do is determine what the domain of the function is and where any vertical asymptotes may occur. The easiest thing to do is to first factor your polynomial there. So if we factor a 3, you would have x squared minus 4. And in the denominator, you can't factor out a 2, but you can factor that as a trinomial and you would get 2x minus 5 and x minus 2. So the numerator has a difference of squares, so that's going to be x minus 2, x plus 2. Now, the domain is going to be x such that x is not equal to 5/2 or 2. So it's going to be all real numbers except 5/2 and 2, and I got that by just setting the denominator equal to 0. Do that first, but you can see that the x minus 2's would cancel here. You would have actually a hole in the function, not a vertical asymptote there, because if you plug 2 in, you would have 0 over 0, not non-zero number over 0. So you end up with 3 times x plus 2 over 2x minus 5. So now we take the limit as x approaches 5/2 from the right of g of x, and we want to take the limit as x approaches 5/2 from the left of g of x. As x approaches 5/2 from the left, the limit's going to end up being negative infinity, and from the right, it's going to be positive infinity. It's important to show that the limit is infinity or negative infinity. Point is that we would have vertical asymptote at x equals 5/2. And then for your horizontal asymptote, you take the limit as x approaches infinity of f of x. And since the numerator and denominator have the same degree, it's just the ratio of the leading coefficients, it's going to be 3/2. And whether you do positive or negative infinity, you're going to get 3/2 either way. So you have a horizontal asymptote at y equals 3/2. So here we have the graph of g. Notice I've put the horizontal and vertical asymptotes on there, and you can see them superimposed on the graph to verify that we actually have those asymptotes. Also notice if I drag down to where x equals 2, you can actually see the undefined point where the hole in the graph would be. All right, guys, that's it for this section. Hope that was helpful to you. As always, reach out if you have any questions, and take care.